Good morning once again. We are going to start with a new topic today, which is confidence interval for population variance sigma square. And the standard deviation is sigma, This is a topic, technically, we don't need to cover it. However, I will be doing it, okay? It's not part of the syllabus, because syllabus has changed, but I kind of would like to have you work on it so that you know it. It's not a big deal. It's rather simple. So I'll go ahead and do it. So by now, you are pretty familiar with how to find confidence interval for population proportion and population mean. And you remember P, we have P, M, S. P is for proportion, M is for mean, and S is for standard deviation. So in the structure of PMS, we did the confidence interval for population proportion, confidence interval for population mean. Now we are going to do confidence interval for population standard deviation. Okay. Now, standard deviation of the population is denoted by sigma. Okay. Standard deviation of the population is denoted by sigma. Now, variance, as you know, it is the square of the standard deviation. So this is the standard deviation, and this is the variance. This is the variance. Now, technically, we know that from sample statistic, we go into population parameter. So in statistics, like how you take X bar, from that you try to approximate mu, right? You take P hat, from that you try to approximate P, population proportion. X bar is the sample mean, from that you kind of approximate population mean. P hat is the sample proportion, from that you try to approximate population proportion. And similarly, S is the sample standard deviation. From that, you try to approximate sigma, which is the population standard deviation. But as we know, S is not an unbiased estimator of sigma. Okay, that means it's a biased estimator. Basically, what it says that in theory, you cannot really use S as an estimate of sigma. However, S square, which is the variance of the sample, is an unbiased estimator of the sigma square, which is the variance of the population. This is an unbiased estimator of this variance. So that's what we are going to do. We're going to find that estimate for or create the confidence interval for population variance, and from that we'll take the square root and find the standard deviation confidence interval. Now here is a little bit of a interesting thing here. This is the formula that you used. Where am I? Yeah, right here. This is the formula that you used to find the sample standard deviation. You probably do remember. S is equal to summation x minus x bar whole square, all of it divided by the sample size minus 1, and you take the square root of the whole thing. Now, if you square it, you're going to get S square is equal to just 1 over n minus 1 times summation x minus x bar whole square. Now, if you square both sides, you get S square here, and square root is going to cancel. You're going to get this, which is whatever is here, right here. Now, you can kind of, okay, without going into detail, you can kind of think of it as S square, this is 1 over n minus 1, that's a fixed number. S square kind of has a distribution that kind of looks like, if we call this something like, let's for the sake of argument, call x1, x2, x3, okay? So this difference squares is, let's call it x1, all right? Even though technically I goes from 1 to n here, there is a symbol here. We are not going to get into the details of it, just for simplicity. You can call it x1, x2. Or if you don't want to call it x1, x2, you can call it something else. Z1 square plus, oh, I shouldn't be using the symbol Z. That might confuse you with what is another xy, let's say y1, okay, for simplicity. Y1 square plus y2 square, okay, plus dot 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 plus yn square. So the distribution looks like this times 1 over n minus 1. This, by the way, is called chi-square distribution, okay? When you take bunch of independent random variables and you square them and you add them, okay? The distribution that you got is called chi-square distribution. And this is a special case of a general function called gamma function. Okay. This is a special case of a general function called gamma function. But we don't need to go into the details of this, but just for the sake of argument, think of this. If you have x1 square plus x2 square plus dot 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 plus xn square, okay? This kind of approximately has a distribution. These are independent and identically distributed random variables. So x1 is an independent random variable. It has its own distribution, bell shape assuming, and x2, x3. If you do take all of this into consideration, the distribution you get is called chi-square distribution. Chi-square distribution. This is more of a theory, by the way, and I don't want you to be too concerned about the theory as much because this is beyond the scope of this class. But I just give a little bit of flavor of it so that you guys can get a sense of what it is. So other than that, if it makes sense, good. If it doesn't, just you may want to look at this description a little bit, but if it's over your head, don't spend too much time because I'm not going to be asking you anything from this, but it would be nice to know the theory behind it, how it works, why it works, okay? And chi-square distribution, by the way, don't think it as a square, some symbol. This is chi, right? It's spelled C-H-I, chi, Greek letter chi. Chi-square, it doesn't mean that chi times chi or anything, it's just a name. All right, chi-square distribution. Now, let's move on to the next page. The way we will find, so I go over all these things here, so look at it. Confidence interval, so this is the formula that you'll be using. Confidence interval for population variance is n minus 1 times s squared divided by chi-square sub r is less than sigma square is less than n minus 1 times s square divided by chi-square sub l. This may sound a bit confusing and too hard, but it's really actually easier than the last calculations that we did. All you need to do is know how to find this value and this value. You already know what is n, you already know what is s squared. Therefore, you have all the things that you need in order to find the confidence interval for population variance. Remember, variance is square of the standard deviation. Variance is square of the standard deviation. All right. Now, let's go ahead and continue. We're going to start doing a problem. All right. It's assumed that the population standard deviation for the number of hours students at your school study, there is a word missing here. Student at your school study is 2 hours. Okay. So it's assumed that the population standard deviation for the number of hours students study at risk is 2 hours. Okay, you take a random sample of 10 students and find that the sample standard deviation is this. Find the probability that your sample standard deviation would be greater than 2.5. You need to find the chi-square R statistic and find the looks like I made this problem harder than it should be. Okay, ignore this one. This should not be the first problem. I need to do something simpler before I can do that one, or maybe I won't even do it. It's a little bit harder than what we should be doing. Okay, so please ignore that problem. Let's do this one. That's probably the easier one. On the average, student at your school spend 20 hours per week studying. You take a random sample of 10 students, find that the sample standard deviation is 3 hours. Create a 95% confidence interval for the population variance. Assume that the population is normally distributed. So here, one of the assumptions is that population has to be bell-shaped, approximately bell-shaped. And this is somewhat of a stronger assumption, okay? You kind of have to assume that population is bell-shaped. Otherwise, your test is not gonna work. So this is a bit of a stronger assumption for the confidence interval for population standard deviation. Now, let's go ahead and work on it. We are going to use this formula. N is the sample size, which is 10. N. Sample standard deviation is S, which is 3. You need to create a 95% confidence interval. Okay, so your alpha is going to be 1 minus 0.95, which is 0.05. Okay, now alpha over 2 is going to be 0.05 over 2. So alpha over 2 is going to be 0.025. Now, previously, we have had bell-shaped curve like this. And we had half of it going to the left, which is 0.025. Other half going here, and that's 0.025. We have the exact same structure. However, this time we are not dealing with a bell-shaped curve. We are dealing with a different type of curve. It is called chi-square distribution. And this is how, folks, chi-square distribution looks like. It is skewed, okay? It is skewed, so sort of skewed to the right. Okay, so you start at 0. Remember, distribution of x1 square plus x2 square plus ... plus xn square. Distribution of all of those guys cannot be negative because it's all square, right? So that's why chi-square distribution starts at 0 and goes to infinity. Now, exactly like the way we did here, we are going to have area to the left 0.025, and somewhere here area to the right is also 0.025, and this value is called chi-square sub L, L for left, and this value is called chi-square sub R, R for right. So this is the basic difference between the bell-shaped curve or t-distribution that we have dealt with so far. Chi-square distribution is stretched to the right, and it never goes below 0. That means it doesn't go to the left. Like this is the normal distribution, this is 0, and these are negative values on the left, and these are positive values on the right. So normal distribution goes from negative infinity to positive infinity, right? That's what the domain of this function is. However, the domain for this guy, however, is not from negative infinity, but rather from 0. This is where it starts, and it goes up all the way to positive infinity. Okay? It goes up all the way to positive infinity. All right. Now, that's what it is. The main thing here is actually finding this chi-square sub L and chi-square sub R values. And what I'm gonna do, I'm gonna take up this and I'm gonna go back to our table. We have a chi-square distribution table. Chi-square distribution has degrees of freedom, okay? Okay, there it is, degrees of freedom, which is n-1, meaning sample size -1, like the way you dealt with the t distribution. Chi-square distribution has degrees of freedom, which is n-1. N is the sample size. So they didn't give a nice cute picture of chi-square distribution here. They should have. Okay. Oh, am I looking at the right table? I'm looking at the right table. I thought somewhere they would give a nice table for chi-square, I mean, nice figure for chi-square distribution. They didn't, but it's okay. Let me bring back my thing. Chi-square distribution has an interesting property. This is something you must pay attention to. So everybody, please pay attention to this, because this is where students go wrong. Normal distribution, what it does, it gives you, when we are talking about area, if you want to find this value, you're going to look at the area to the left. Okay, if you want to find this value, you're going to look at the area to the left of that point, which means that it is cumulative from the left. It's cumulative from the left. However, chi-square distribution is just the opposite. It's cumulative from the right. Chi-square distribution is just the opposite. It is cumulative from the right. Okay? What it means is that if you want to find this point, you're not going to look at the area to the left, but rather you're going to look at the area to the right. If you want to find this point, you're going to look at the area to the right, not area to the left. Area to the left is 0.025, right? Area to the left is 0.025. But to find this particular point, chi-square sub L, you need to look at the area to the right, which would be 1 minus 0.025, which is 0.975. So you're going to be looking at the area under the curve to the right to find this point, which would be 1 minus what is to the left. Okay, to the left is 0.025. So 1 minus 0.025 is 0.975. And to find this point here to the right, this one, we are looking at the area to the right, which is already 0.025. So that's what the thing is. Now let's go ahead and find the table. find these values on the table. Now look at this table. The first column is the degrees of freedom. Our degrees of freedom is n minus 1, which means 10 minus 1, 9. So we are going to be looking at row number 9. Now, to find the area to the left, what we need to do, we need to look at the, chi-square sub L to find the area. To find that value, we need to look at the area to the right. Chi-square, so let me, well, I can't bring the picture back right now, but it would be the area that I showed you to the right, which is 0.975. So if you look at 0.975 column, you can see it comes to 2.7. Okay, one is 2.7. Now for the other one, you have to look at 0.025, and 9 is gonna give you 17.535. And this is a problem that I have done, so I already have it here, okay? So let's go back to the problem. You have these values. Okay. It is right here. Chi-square sub R chi-square sub R, this value is 19.023, and chi-square sub L is 2.7. That's what it is. Now, these values, you just have to find it from the table and then plug it in right here, okay? So if you plug it in here, you have the chi-square sub R and chi-square sub L. N is 10 and S is 3. So you just do the multiplication and calculation, you end up getting 4.25 is less than sigma square is less than 30. If you take the square root of everything, then you're gonna get what is the square root of 4.25? 4.25 square root is gonna be 2.06. 2.06, okay, is less than sigma, is less than 30 square root is 5.47. 5.47. So the confidence interval for population standard deviation is 2.06 to 5.47. And for the variance, it's this number. I think there is a typo here somewhere. Why is it 33.77? There is a typo somewhere. So please check it, okay? This is incorrect. Just check this calculation. You know, I'll just do it for you. So 81 divided by 19.023. 81 divided by 19.023, which is 4.25, correct? So 4.25 is less than sigma square is less than 81 divided by 2.7. 81 divided by 2.7, which is 30. Okay, so this looks about right. So somehow this is not right. So that's how you'll find the confidence interval for a population standard deviation. So you, in essence, find the confidence interval for variance, and then you take the square root of it. All right, that's how you'll do it. This is a bit complicated looking, but it's not really as bad as it looks. Okay, this looks a bit, oh, there it is, 5.48. Just looks a bit complicated, but it's not as bad really. Any question, anybody, before I move on to the next problem about this one? Anybody has any questions? Anybody not clear on anything in the process? Everybody's okay? Okay, if there is no questions, I'll continue. I'm gonna go ahead and start working on the next problem. Now, this problem should be pretty straightforward, okay? Exactly like the last one. Exactly like the last one. Now, I even give you the formula right here. You just need to fill in the blanks. In the agricultural city of Salinas, California, you surveyed 13 people, okay, field workers, and find that their income is $17,000 per year. So you surveyed 13 people, you find that the average income is $17,000 per year with a standard deviation of 3,000. That is the sample standard deviation, okay? Based on this information, create a 95% confidence interval for the population standard deviation of the income of the ag field workers. Assume that population is normally distributed. So this is one of the assumptions which has to be kind of strong in this case for the calculations to have any meaningful meaning. Make sure that this assumption holds true. The distribution of the population is approximately bell-shaped. So make sure that that holds true. Otherwise, the calculations don't make a whole lot of sense. Okay. So basically, you went out in the field. So you went to the field and asked 13 people, hey, how much you make? How much you make? And you found that their average is $17,000. And you also did the standard deviation calculation, and you found it to be $3,000. Okay, now the question is, how do you create a 95% confidence interval for the population standard deviation? Now we have to first find the confidence interval for population variance, which is sigma square, and then we take the square root. Let me fill in the blanks here. We have n s chi-square sub r, so n s chi-square sub r and chi-square sub l. N is the number of people you surveyed, which is 13. Okay. S is the standard deviation of the sample. So S is the standard deviation of the sample, which is 3,000, is given to you here. Now, chi-square sub r and chi-square sub l. For you to find that, first you need to find alpha, which is 1 minus the confidence level, which is 95, which is 0.05. So alpha over 2 is going to be 0.05 over 2, which is 0.025. So alpha over 2 is 0.025. Alpha over 2 is 0.025. So if we were to draw the chi-square distribution, remember chi-square distribution is stretched to the right. So it's going to look like this. Not a good chi-square distribution drawing. Make it a little smoother looking. Okay. Area to the right is going to be 0.025, and let's say area to the left is going to be 0.025, and this is your chi-square sub L, means left side, right? And this is your chi-square sub R, meaning the right side. And what is our degrees of freedom? df is equal to n minus 1, which is 13 minus 1, which is 12. N minus 1, which is 13 minus 1, which is 12. Okay. Now we have all the things that we need in order to solve the problem, except these two values, this one and this one, which is this and this. We go back to our tables, okay? Closer attention. First time around, if it didn't make sense to you, it will start to make sense this time around. So let's look at the table. Okay. Chi-square distribution, look. Degrees of freedom is 12. So we are gonna look at 12, row 12. And area to the right is gonna be 1 minus 0.025, which is 0.975 for this chi-square sub L. So 0.975 is gonna give you 4.404, 4.404. And area to the right is 0.025, which is this, and this is gonna give you 23.337, 23.337. Okay. Now let's go back to the problem. Okay, so that's the problem. Now we have the values that we need. So our formula is n minus 1 times s squared divided by chi square sub r is less than sigma square is less than n minus 1 times s squared divided by chi square sub L. N is 13 minus 1 times S is 3000 square divided by chi square sub R, which is this value 23.337 is less than sigma square is less than 13 minus 1 times S square, which is 3000 square, all of it divided by chi square sub L, which is 4.404. Now we just need to simplify it. Okay. So if we simplify it, what do we get? 12 times 3000, 12 times 3000 divided by, square 3000 to the power 2 divided by 23.337, which is roughly about 46, 844 roughly is less than sigma square. Then the right side gives you 3000 times 3000 times 12 divided by 4.404, which gives you 245, 23160. Okay. And if you take the square root of that, you're gonna get 49, 52 roughly, and square root of this 46 was 4,627,844. Square root of that is 2151. Okay, that's what it is. So standard deviation falls between 2151 and 4952. And how confident are you in your calculation? About 95% confident. So what does that mean? It means that if you took a sample of the same size of 13, many of them, and from each of them you create a confidence interval like this, about 95% of those confidence interval will include the true population standard deviation, and about 5% will not. And that's what it is. So this is how you will do confidence interval for population standard deviation. And it is a very standard process, okay? It is a very standard process, and you just need to follow this. And keep in mind that chi-square distribution, okay? Chi-square distribution is cumulative from the right. And one of the things I do notice, sometimes students get this value and they square it because there is a square here. Please note that the name is chi-square. That's how we write it. It is not squaring a variable called chi. It's just a name, chi-square, okay? So don't square these values. This is a very simple problem, but you have to see it a couple of times before you get comfortable with it. Anybody has any question on this so far?
No questions.
Okay. All right, so that kind of concludes this handout, okay? So now we are going to start with the new handout. Now we are going to talk about hypothesis testing. What is hypothesis testing? Hypothesis testing is testing the testing some characteristic of the population, okay? When you're doing hypothesis testing, you are testing some property, attribute, or characteristic of the population. For example, you could be testing the average for the population. So let's say on the average, people work 40 hours per week, okay? In the US, people work 40 hours per week. This is a known fact. You might be testing it, okay? You might be testing the assumption that on the average, people work 40 hours per week or 8 hours per day, whatever way you do it, okay? 8 hours per day. So you may be testing that. Or you may be testing something like what percentage of the people, okay? So you might be testing population proportion. What percentage of the people believe in Black Lives Matter movement, okay? That could be a testing that you should be doing. What percentage of the people believe in Black Lives Matter or right for Black people in this country? So that's testing for population proportion. Or you could be testing the standard deviation. Think of another situation. Let's say two different manufacturing companies making iPhones, okay? Two different plants, not two different manufacturing companies. Let's say the same company, they have two plants where they make iPhones or iPhone maker, two iPhone makers. You compare the standard deviation, which one has higher standard deviation, okay? compared to the other, or which one has lower standard deviation, or you make some assumption, or you make some calculations to determine the population standard deviation, or approximate the population standard deviation. So we will be doing the PMS thing again. Remember, proportion, mean, and standard deviation. We are going to be doing testing about population proportion. Okay, we are going to be doing testing, hypothesis testing. That's what I mean, for population mean. We are going to be doing hypothesis testing for population standard deviation. So these are very useful testing, and please do keep in mind, in the real world, hypothesis testing is very important. People do hypothesis testing in different contexts, in manufacturing, in social studies, in medicine, in many fields. Pretty much, statistics is a subject that's applicable to pretty much anything under the sun. All right, but there are big scenarios. As a manufacturer, you might be interested in what is the average production time. So in that case, you're testing for mean, okay? And the same manufacturer might be interested in what percentage of the product being shipped are good quality product, or what percent of the product being manufactured is good quality product. Or the same manufacturer might be interested in finding the standard deviation of a certain product, standard deviation of, let's say, number of hours that they spend in making the product. So why is standard deviation important? You want to find out whether there is strong variation in the amount of time spent in building a product or manufacturing an item. So these three things could be used by one individual corporation or one individual company. You know, like COVID-19 right now, you can think of it, okay, how long is the effectiveness of COVID-19 vaccine that people are taking? Okay, how long is it good for? That's like you're doing the M, mean, right? How long is it good for? That's the mean. What percentage of the people are being vaccinated are staying healthy, or the effectiveness of the vaccine? That's the proportion, right? So you can see a pharmaceutical company is already interested in these two things. And also they may be interested in the standard deviation of the manufacturing time, or mean. How long is it taking? How much variation do they have? You guys are interested in finding out, oh, how long is it before we are gonna get the next vaccine? Okay, it depends how quickly they can produce. What is the average time for production? What is the standard deviation for production time? So these are things that you probably don't care as much directly, but the manufacturers do care about them a lot, because you as a consumer, you ask a very simple question: when am I going to get my vaccine? How good is it? These are the basic questions you ask, and everybody asks. Okay, during COVID-19, when am I going to get the vaccine? How good is the vaccine? So in essence, you're asking proportion question. What percentage of the time that this vaccine is effective? When you're asking, when am I going to get the vaccine? That basically depends on how much time they take to manufacture it, right? And standard deviation, you probably don't worry so much directly, but manufacturers do worry about standard deviation. Variation in percentage, okay? Variation in mean, which is the standard deviation square, right? So these are numbers manufacturers are interested in. All right. So we are going to be doing hypothesis testing for population proportion. We are going to be doing hypothesis testing for population mean, and we are going to be doing hypothesis testing for population standard deviation. So PMS structure again. So when we are doing hypothesis testing, we are kind of, so let's see what the official definition I gave you. hypothesis. A hypothesis is a claim about a population parameter. Now, remember, I have been hammering these ideas in your head since day one of the semester. The difference between parameter and statistic. A parameter is a characteristic of the population. A parameter is something about the population, entire population. On the other hand, statistic is a characteristic or something about the sample. Statistic comes from the sample and the parameter comes from the population. So in this chapter, you are doing hypothesis testing. You're testing a claim about some population parameter. Typically, it is either proportion or mean or standard deviation of the population. You may be asking a question about the population proportion. You may be asking a question about population mean. You may be asking a question about population standard deviation. So when you're doing hypothesis testing, you're in essence doing a testing about some property or some characteristic of the entire population. You don't do hypothesis testing about a sample, okay? You always do hypothesis testing about population parameter. It could be proportion, mean, or standard deviation. All right, next, when you are doing hypothesis testing, there are two types of hypotheses. So it's one or the other. One is called the null hypothesis. Another is called the alternative hypothesis. Now, what is null hypothesis? Okay, null hypothesis is a hypothesis that is given, something already known. So null is the default. Okay, null is the default assumption. Okay, so let's say we know that in the general population, 67% of the people support abortion, let's say. Okay, 67% of the people support abortion. So that would be the null statement. That means it's given. Now, you as a researcher or you as a consumer of information, you might be interested in finding out the validity of these assumptions. So they are saying, people are saying that 67% of the people in the population support abortion. Now you want to test it out. Is it true? Or is it something that you would accept? We don't technically ask the question true. Is it something more acceptable? Because this is statistics, whether it's acceptable versus not acceptable. So that's what it is. Or for the Black Lives Matter, let's say 70% of the people support Black Lives Matter. All right, 70% of the people support Black Lives Matter. So this is something you want to test. This is something you want to test. All right, and 70%, the given number is the null hypothesis. This is something given to you. Another way to think about this is the American justice system, okay? Which is, in theory, this is how it's supposed to work, but in reality, I don't know. You are innocent until proven guilty, okay? That's the theory, okay? You are innocent until proven guilty. So that means by default, a person, if a charge is brought against a person, by default, the person would be considered innocent. That is the null hypothesis. Innocence is the null hypothesis, and the alternative is going to be guilty. Okay? Innocence is the null hypothesis, and alternative is the guilty. So remember, to summarize, null hypothesis is the default assumption or given assumption about the population, okay? And alternative hypothesis is the one which is opposite of that or complement of that, okay? Innocent is the null hypothesis given assumption. Alternative is guilty. 70% of the people support Black Lives Matter. I wonder what the other 30% is thinking. Oh, by the way, this 70% I made up. I'm assuming that it's 70%. Okay. 70% of the people believe that Black Lives Matter movement should be supported, or which is basically supporting equal rights for Black people. And then this is the null hypothesis. That means 70%. This is given to you, or this is what people commonly believe. Then the alternative would be it is not equal to 70%, or it could be another option would be it's greater than 70%, or it is less than 70%. These are all different options, right? So you test against the null hypothesis, and alternative is the complement of it typically. Okay, alternative is the complement. So if you're testing for Black Lives Matter, I should make a problem actually on this. Maybe I'll do it for the final exam, since you just had the midterm. One is Black Lives Matter, another is COVID-19 problem. These two are the issues that rocked 2020 lives of Americans in the year 2020, Black Lives Matter and COVID-19. And the COVID-19 actually rocked the lives of people all over the world. Black Lives Matter in the US only, or mostly rather. So maybe I'll make up two problems on this. And it is kind of surprising. Honestly, as a human being, I'm ashamed that we still have to do these things like Black Lives Matter movement, things of such fundamental right, people are being violated and not given their rights at this time. I am, as a human being, I am really ashamed that our intellectual capacity is not there yet. This is shameful, but I don't control the people. Anyway, back to our problem. All right, so next, let's see, what do we want to do? Okay, when you are doing hypothesis testing, you're typically dealing with three different scenarios, okay? Now always includes some statement, which is equality. Now, so remember this, one way to identify null hypothesis, it will always include the equality side, okay? That means something is something, okay? Somebody is innocent, okay? Or Black Lives Matter, people support is 70%, is, okay? That means equal to 70%. So if Black Lives Matter is 70%, we are talking about proportion, right? So P is 0.7, that is your null, which is denoted by H naught. And sometimes alternative is denoted by either H1 or H sub A. I use H sub A, okay? Null hypothesis will always have this equal sign, okay? It will always have the equal sign. Alternative, on the other hand, will never have equal sign. Never equality, okay? So you don't want equality for alternative. So what could you test? Some population parameter theta is greater than some value A. Some population parameter theta is less than some value A, or some population parameter theta is not equal to A. When I say theta, okay, theta is the population parameter. In our case, this theta would be coming from this P, M, or S. Theta would be one of these three. Some population parameter. So this is the generic name. Theta is the generic name for some characteristic about the population. And in our case, population proportion, population mean, and population standard deviation. This is what we are talking about mostly. Now, test statistic, critical region, and all of these things, I'm going to actually talk about it as I do a problem. Now, if I talk about it, it may not make a whole lot of sense, but I'll just give you a brief overview. Test statistic is some value that you get from the sample, okay? Based on the calculation, okay? Test statistic is some value you get from the sample data that you collected and in conjunction with standard normal distribution table, okay? And critical region is also something that you get from the significance level, okay? Significance level tells you how confident are you, or technically significance level tells you what are the chances that you are wrong, or equivalently, how confident are you? If significance level is 5%, that means 5% of the times you will be wrong. That means 95% of the times you will be right. So that's basically what it is, significance level. This may sound a lot of information right now. Don't worry about it. It's okay. We are gonna solve problems. Once I solve many problems, which I will be doing, then it will start to all sink in, okay? Now, just remember, you will be doing hypothesis testing, and null hypothesis always includes the equality. Alternative never includes the equality. There are three types of alternatives you could be testing. One is either population parameter greater than some value, less than some value, or not equal to some value, okay? If it is greater than, you're going to be doing right tail test. If it is less than, you're going to be doing left tail test. If it is not equal to, you'll be doing two tail or both tailed test, okay? Left tail, right tail, or two tail or both tailed test. That's what you'll be doing. Is this clear, everybody, so far? Okay. Now, let's go ahead and talk about a couple of interesting things. When you're doing hypothesis testing, you can make mistake. Think of, what if somebody innocent? Somebody is innocent, but you find him guilty. That means you send the person to jail, even though the person is innocent. You made an error, okay? This is called type 1 error. Think of the justice system. That's easier way to kind of remember this thing. Somebody innocent, you send a person to jail. That means you made a mistake. That's type 1 error. And type 2 error is the opposite of it, which is somebody is actually guilty. That should be the verdict, right? Guilty, but you exonerate the person, okay? Or you say that, oh, he's not guilty, okay? And that's called type 2 error. You exonerate the person. So that's called type 2 error. And I created a table here. H naught is true, meaning the null hypothesis is true, meaning the person is innocent. But you reject the null hypothesis, meaning that you find the person guilty. So if you take an innocent person, but the justice system finds him or her guilty, then the error committed is type 1 error. On the other hand, H naught is false. What does that mean? That the person is guilty. That means guilty. The person is guilty. But if the person is guilty, what should you do? You should reject the null hypothesis that he is not innocent, but you don't, okay? You do not reject the null hypothesis that the person is innocent. You also created another type of error. In this scenario, it's called type 2 error. Now think of this as a bell-shaped curve. Type 1 error would be like the significance level. So remember, if middle is less than 95%, okay, this is 0.025, 0.025, okay, 100%, or 0.95. So type 1 error is associated with significance level, which is this or this. On the other hand, type 2 error is the middle one. Type 2 error is more difficult to find out, okay? Type 2 error is more difficult to find out. Well, so we don't talk about type 2 error. There is a whole field of study about finding type 2 error. But think of the justice system. Many people commit crime, they actually get away with it. That is type 2 error. Because technicality, sometimes I see in the justice system, because of technicality, somebody does something and they get away with it. Okay, for example, evidence was not collected in a timely manner, or this or that. And type 2 error is very serious. I mean, more common, I think, in the justice system. If you have a person who is, let's say, African American or Black, more likely to be a victim of type 2 error. Person probably hasn't done it, but still would be convicted. There are many cases in our justice system for that. On the other hand, there are people who just get victimized because of the system, because of how they are treated. But that's another social issue. We are not going to talk about it so much. Let's talk about the type 1 and type 2 error. Type 1 error, when null hypothesis is true, you reject. Type 2 error is when null hypothesis is false, you don't reject it. Okay? All right. Yeah, now please read it. Read this couple of pages. I talk about it in details. Now, let's start off with hypothesis testing for population proportion. These numbers, I think, are 10. I forgot this. So for the sake of safety, make it 10. NP is greater than or equal to 5. I mean 10. N times 1 minus P, or NQ, also 1 minus P is also known as Q sometimes. So N times 1 minus P is greater than or equal to 10. And what does this do? It ensures normality. It ensures normality. So it makes it bell-shaped. For population proportion, distribution of population proportions to be bell-shaped, we need to make sure that N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. That makes sure, or that ensures, that population is normally distributed. Population is normally distributed. Okay. So this is a generic structure of hypothesis testing. Step 1, you'll be ensuring that the normality condition is met. So make it 10, guys. I think it's 10. There was a typo here. NP is greater than or equal to 10, and NQ is greater than or equal to 10. All right. Now the null hypothesis and alternative hypothesis. Null hypothesis is this, and alternative could be one of these three. And the test statistic, how you derive the test statistic, we don't go into the details of it. You just take it as it is, all right? So basically P hat minus P divided by PQ over N, it has standard normal distribution. That's what you can assume. And next, once we find the test statistic, we are going to find the critical regions, okay? And based on the test statistic and critical region, we are going to make a conclusion, and then we may talk about p-value. In the industry, they really don't make you go through all these steps, but I make you go through all these steps because you're learning. You need to know how it works, okay? In the real world, what you're going to do, you're assumed, it is assumed that you know what does p-value mean. By that, you know exactly what it is, all right? So you need to learn it, the process in the industry, or if you actually do a project, somewhat of a large project, you'll be using the software. There are a lot of statistical softwares that you can use that's just going to give you right away the p-value if you give it the significance level, okay? And we'll talk about it. All right, so let's do a problem. So the first problem, I actually did it for you. What a coincidence. This is a problem I made many years ago, and very pertinent to what's happening right now in our country. Black Lives Matter. Roots, a very popular TV show in the 1980s that depicted the lives of African Americans in the US. You want to know whether the majority of the people nowadays have heard about this TV show. You surveyed 350 randomly selected people, and 190 of them said that they have heard of or seen the show. Based on this data, would you reject the null hypothesis H naught? Okay, null hypothesis H naught is P is equal to 50% at 0.05 significance. Okay, 0.05 significance level. All right. So I give you the null hypothesis that half of the people, or 50% of the population, knows about this. So this is what you're testing. This is what your null hypothesis is. Okay, this is what you're testing. This is what your null hypothesis is. And please make this correction, make it 10. Make it 10 to be on the safe side. Now your N is so now starts the actual process of hypothesis testing. Make sure that you follow along. And first couple of, or maybe 3-4 problems may sound a bit difficult, but once you do the first 3 or 4 problems, you will start to get comfortable with it. In the next class, I'll do more problems of this type, many of them, so you will get the hang of it. And in the final exam, which is about a month from now, you will be asked a lot of questions about hypothesis testing. Make sure that you understand it. So the null hypothesis, so first the requirement. So the requirement is, sorry, it's not that one. Requirements. N is the sample size, P is 0.5. P is 0.5, I gave you. That's what people believe, that half of the people roughly knows about the TV show Roots, which was popular in the 80s. Okay, N is 350, P is 0.5. So N times P is 350 times 0.5, which is 175, right? Obviously, that is greater than or equal to 10. Similarly, N times 1 minus P, which is 350 times 1 minus 0.5, that's also 175. That's also greater than or equal to 10. So both of the conditions, that NP is greater than or equal to 10 and N times 1 minus P, or NQ, is greater than or equal to 10, both of these conditions are satisfied. Therefore, the distribution of the proportions, okay, distribution of the sample proportion is Bell shaped, okay? Or the sampling distribution is bell shaped. Remember, it cannot be assumed that, oh, one of them works, but the other doesn't. In that case, you cannot assume normality. It has to be both, okay? One or the other does not work. It has to be the case both of these conditions are satisfied. When both are satisfied, both of them are satisfied, that's when you can assume that it is bell-shaped. So step one, requirements. So we did it. The null and alternative hypothesis. The null hypothesis is that is given P is 0.5 or 50%. P is 0.5, which is the same as 50%. You're saying that it is 50%. Alternative is going to be complement of null, which is P is not equal to 50%. It's like innocent, guilty, okay? P is 50% or P is not 50%. But you may be testing for other things too. I have designed the problem this way, but you could be testing for other things. You could test that P is greater than 50%, that's an option too. Or you could have tested that P is less than 50%, that's also an option too. You could test any of this. Remember, once again, null hypothesis always includes the equality sign. So that's the null and alternative hypothesis. That means two statements, two complementary statements. Test statistic. So this is where you find Z star, I label it by Z star, which is P hat minus P divided by square root of PQ. Q is, by the way, 1 minus P, okay? This Q is 1 minus P. All of it divided by the sample size N. This has approximately normal distribution with a mean of 0 and a standard deviation of 1, okay? That's why we use the Z star. Now, P hat, remember, P hat is X over N, which is 190 people said that they heard of the show out of 350. So it's going to be 190 divided by 350, which is exactly what I've got here, minus 0.5, divided by the square root of 0.5 times 1 minus 0.5, which is P times Q, divided by the sample size 350. If you do the math, you get 1.6. So your test statistic Z star is 1.6. Now the critical region, all right? So I have to clean up the screen. For critical region, I'm gonna draw this bell-shaped curve with a mean of 0 and standard deviation of 1, 0 and 1, which tells you that it is standard normal distribution. It tells you that it is standard normal distribution. Okay. Now, let's go ahead and find out which tail are we testing. So our significance level is 0.05. So alpha is equal to 0.05 significance level. Remember how we found alpha in the last chapter? It was 1 minus the confidence level. So that's the significance level. They are gonna, so this alpha will be distributed either in one tail or in two tails. Whenever you have not equal to, so let me bring back the thing here we talked about. There, where is it? So right here, look. If it is not equal to, you have to do two-tailed hypothesis testing, okay? If it is not equal to, we are testing not equal to, okay? So two-tail testing, all right? Now, two-tailed means you have to divide it into 2. So alpha over 2, which is 0.05 divided by 2, which is 0.025. So your area to the left, so this area to the left is going to be 0.025. This area to the left is 0.025. This area to the left is 0.025, and that area to the left is 0.025. That means this significance level get distributed into 2 sides. Why is that the case? Because we are testing, I need to go further down. Right here, that's where I was at. Okay. Because we are testing not equal to means, so population proportion is 50%. Not equal to means it could be greater than 50% or it could be less than 50%. So we are gonna go ahead and find these 2 critical values, which is easy. By now, you know how to find these values, and it is one of the very standard values. This is negative 1.96. If you look it up in the table, you just took the midterm, you know it. Area to the left in the standard normal distribution curve is gonna tell you the associated z-score. So in this particular case, area to the left is 0.025. Associated with that is the z value, negative 1.96. And by symmetry, remember, bell-shaped curve is symmetric. And by symmetry, this is going to be 1.96. Or you can look it up on the table too. Area to the left of this point is 0.975, and it'll give you 1.96. So your critical region, okay, your critical regions are going to be everything from negative 1.96 to positive infinity, everything from positive 1.96 to infinity. And that's exactly what I say here, negative 1.96 to negative infinity to negative 1.96, and from 1.96 to positive infinity. So these are the regions. Let me just sort of like highlight it so that you can see it. So these are the regions we are talking about, highlighted regions. Maybe blue would be better highlighting. Okay, so these are the regions that we are talking about. Now, if your test statistic z star is 1.60 falls in either this region, which is to the left, or this region to the right, you will reject the null hypothesis. You will reject the null hypothesis. And let me use red so that you can see it here better. 1.6 is a positive number, so it cannot be to the left of 0. 1.6 is a positive number. Is 1.6 greater than 1.96? The answer is no. Okay, so it's going to be somewhere here, 1.6. So 1.6 does not fall either in the right tail, nor does it fall in the left tail. So that means it does not fall in the critical region. My critical region, remember, negative infinity to negative 1.96 and 1.96 to positive infinity. So it does not fall in the critical region. Whenever your test statistic does not fall in the critical region, you do not reject. So remember, you do not reject the null hypothesis H0. If your test statistic does not fall in the critical region, then you do not reject the null hypothesis. On the other hand, if it does fall in the critical region, then you reject the null hypothesis. All right? Now let's go ahead. So that's what the conclusion is. Then there is one thing we didn't talk about is p-value. Okay, I'll talk about it. I don't want to give you too much information at the moment. Too much information at the moment. I already feel like I gave you a lot of information with hypothesis testing. P-value is something I'm going to talk about when we get more of a handle of this hypothesis testing. However, I'll give you a hint. What is p-value? So let's say this is my negative 1.96 and this is my positive 1.96. Okay, my critical regions are from here all the way to the positive infinity, from here all the way to negative infinity, right? And your test statistic was right here, 1.6. Okay, 1.6 was right here. So p-value, okay, p-value is gonna be, since it's positive, we are gonna consider the right side, area to the right. Okay, that is the area to the right. Okay, now if you look at it, this point, this area to the right is 0.025. Okay, this double shaded region is 0.025. If p-value, if a test statistic does not fall in the critical region, what's going to happen is that your p-value is going to be greater than, okay, greater than alpha. In that case, you do not reject the null hypothesis. Why is p-value greater than alpha? Alpha is 0.025, which is just this double shaded region. But p-value is bigger than that. That means because this 1.6 is to the left of 1.96, okay? To the left of 1.96, that means it has this area plus more, which is this, okay? This single shaded region. So that means when p-value is greater than alpha, you do not reject. Do not reject null hypothesis. On the other hand, if p-value is less than or equal to alpha, okay, that means it's either 1.96 or greater, you reject H naught, okay? You reject the null hypothesis. And that's what the entire hypothesis testing process. And in the real world, what you will see more like, you know, you'll be using some statistical software, and if you give the software the corresponding inputs, it will just spit out a p-value, okay? P-value. So if you want to communicate your research between you and, let's say, your colleague who is working on the same project, you'd say, oh, p-value is this and alpha is this. Okay, let's say p-value is 0.075, alpha is 0.025. In that case, the colleague will know that, oh, what you're talking about. In general, you don't go through all calculations, all of this, to find out the conclusions. It is all an automatic process, very, very precisely defined process that could be built into a software package, which is done many, many times. There are many, many statistical software packages. SAS is one of them, I guess. You know, you could use Python packages too, Python. And there is R. R is something that's used more in the academia. Python is more universal. So you may want to explore Python. And if you want to go professionally, you can use SAS or something. There are many statistical softwares, and all of them are basically doing similar type of calculations. And for hypothesis testing, it's so standard. It's so standardized that you can go ahead and just find the p-value right away, quickly. Things that would take you a long time to do by hand, computer will do it in a matter of seconds. And does it mean that you should just go ahead and use the software and find out. Even your TI-84 calculator will do these calculations, hypothesis testing. You give it the data and it will spit out a p-value, and you can conclude. I don't believe in that personally. I want you to learn why you are getting these values and what is the process, knowledge, and understanding that goes behind it. This is very important. I recall vaguely, I saw a YouTube video where back in 1987, before many of you were born, there was a spaceship disaster. It was called Challenger. Okay, we are sending it to the space. It exploded in midair. You may have heard of it. It was a big news all over the world back then. And guess what happened? One of the pieces of metal, it shrunk to the point because of temperature. In the space, temperature is lower. It shrunk significantly. That was the source of the problem. I don't know the detail, but that's what it was. And one of the reasons that they gave was that the statistical calculation that they should have done on that on the expansion and contraction of that metal was not done properly. Okay, and maybe they did something that I really don't remember the whole thing. Maybe I should watch the video again. But they made a mistake in doing the statistical calculations. Otherwise, they would have caught it before the takeoff. And that happened. One of the reasons I'm guessing is that probably they didn't have a thorough understanding of hypothesis testing when they were doing it. If you don't know how the process is done, or what you're testing, what is the null hypothesis, what is the alternative hypothesis, and how it applies to the problem at hand, you just get the p-value and you do the problem, and that's not good. That's actually quite risky because you don't know the theory behind it. You don't know what you're testing. Just imagine somebody doesn't know any of the things, just gets the p-value and alpha, says, hey, yeah, I reject or I don't reject the null hypothesis. That's not good enough. So that's why I strongly believe in showing you the step-by-step process and having you go through this. And every single problem in hypothesis testing, I'm going to have you go through this process. And then you can use your calculator to do your calculation. As a matter of fact, I don't even emphasize the calculator too much on hypothesis testing. Even in the exam, you'll be doing it step by step. All right, enough for the day. I think I have given you plenty of information for the day. So for Wednesday, I expect you to look at this handout, okay? This new handout, and look at the hypothesis testing first few pages. Look at the examples. Read up the first few pages so that you're comfortable with the definition, and then we will do many problems of hypothesis testing covering proportion, mean, and standard deviation. Hypothesis testing for proportion, hypothesis testing for mean, and hypothesis testing for standard deviation. All of this will be done many times, and you'll be very comfortable with the process of hypothesis testing by the time we finish this chapter. All right, I think that's all. I'm going to stop here for the day, and we'll talk to you guys on Wednesday. And be safe and stay healthy. Take care.